This is another type of integral that can vary widely. The idea is that uh, you need to use a different strategy depending on whether or not one of these powers is odd. So if one of the powers is odd, let's say if that were sine cubed or sine to the fifth or something like that, you could easily pull one of the signs out to be grouped together with the dx to use a u substitution. And if the sine is odd, then you could make u equal cosine, right, and use Pythagorean identities. Or if the cosine is odd, the power of the cosine is odd, then you can make u equal to sine, and then things kind of work out that way. But when both powers are even, strategies get a little more complicated than that, and you have to be a bit more creative and resort to other trig strategies. So we are going to use a power reducing formula, or two power reducing formulas, one for sine and one for cosine, which will then result in the same expression. So this is usually how you deal with this type of problem. So here are the two power reducing formulas that you need to remember. The first one will say that the cosine squared of x equal to 1 minus the cosine of 2x equal to 2. This is a formula that is not necessarily easy to remember, right? Here you have square of the angle, or square of the cosine, and then you replace that with some expression that depends only of the cosine of double the angle, right? And if you need to come up with this formula on the spot, I'll explain to you how to do it now. So let's say you start with the cosine 2x formula. You got to remember that this is cosine squared x minus sine squared x. In either case, you got to remember one thing, right? And then you can remember that because sine squared plus cosine squared equals to 1, you can replace the sine squared with a 1 minus cosine squared x. And the right-hand side, you can use distributive property, and then this minus becomes a plus, and then that turns out that you have 2 cosine squared x. And you can already start seeing what's going on, right? You add the 1 on the left side, and then you divide by 2. So that's the easiest way to come up with this formula on the spot if you don't remember it. Just remember the double angle formula for cosine. In a similar way, you can also come up with the sine squared x power reducing formula, which is 1 plus. Or I messed up, but my own formula corrected me. So with cosine you have plus, so let me correct that. See, this is why it's important to know how to get the formula as well. And then the sine is minus, so 1 minus cosine 2x over 2. Easy to remember because the plus, right, goes with the cosine itself. And because these are different, then that's supposed to be a minus. Easy, sort of a mnemonic strategy for you to remember which one is which. Now, how does that help me? When you have these two even powers, you can just rewrite. So again, you don't need this green part. You need these two expressions memorized and remembered. And once you have them, you start the problem by rewriting the sine squared as 1 minus cosine 2x over 2. Instead of actually putting a big over 2, I will put 1 over 2 on each. So that will make my life a little easier. And then the cosine squared is 1 plus cosine 2x over 2 dx. So we end up with an expression in which the only unknown expression here, the only variable or the only expression that depends on x is cosine of 2x. Right, so 1 minus cosine 2x over 2 and 1 plus cosine 2x over 2. So this is the only thing that is not just a constant. Right? So how do I make this work? How do I make this work? I start by expanding that. Expand this and expand this using distributive property or just basic foiling. Or if you remember, this is the difference of squares. This is a minus b times a plus b, which is a squared minus b squared. So it turns out that this is the integral of 1/2 squared minus cosine 2x over 2 squared. So this is the integral of 1/4 minus cosine squared 2x, also times 1/4, because the 2 at the bottom. So we can split this up into two integrals. Integral of 1/4 minus 1/4 the integral of cosine squared 2x dx. This first integral is pretty simple, pretty easy to solve. Integral of 1/4 of 1/4 dx is just 1/4 of x. Right? If you derive this, you can easily see that the result will be 1/4, and then plus 1/4. And now we have another problem, which is the fact that this is another even power. So you have to resort to the same strategy again. This is going to be a common theme whenever you use this type of power reducing formula. You're going to probably have to do it again. So this is going to resort to a problem in which, look, you start with the cosine of an angle, and you get this expression with double the angle, right? Now, because you already have double the angle, you got to double the angle again to use the formula. So you're going to end up with 1 plus the cosine of 4x over 2 dx. And I'll actually, again, put a 1 over 2 on each, because that's going to make my life a little easier. One way to see this easily, if you want, is to maybe call this 2x equal to some other variable like theta or something, and then write the expression as cosine squared of theta equal to 1 plus cosine of 2 theta over 2. And then because theta is 2x, right, then this 2 theta is 4x, which is why we get this 4x right here. But that's only if you need a little reminder of what to do, of how to handle this. The main takeaway is to remember that the angle doubles when you use a power reducing formula. It's the price you pay. You reduce the power, and you have to pay the price. The price of doing business here is doubling the angle. Reduce the power at the cost of doubling the angle. So now we continue our expansion. This 1/4 x doesn't change at all. And then I have a minus 1/4 the integral of 1/2 dx minus the 1/4, because this 1/4 is multiplying the whole thing, right? And then I can have a 1/2 on the outside, this 1/2 coming from this 1 over 2 in front of the cosine, integral of cosine 4x dx. So now this is fine. Now this is almost perfect, because if I continue writing, this is going to be just 1/2 of x, right? And then times 1/4, it's going to be a 1/8 of x. And this will be another 1/8 times the integral cosine. So cosine of 4x. You can do this without writing too much at this point. At the end of a calculus class, a calculus 2 class, when you're already learning this type of power reducing formula, you can already not write as much when you do u substitution. But that is the trick here, to use a u substitution that involves u equal to 4x, du equals to 4 dx. So 1/4 du is dx. So this integral turns into a cosine of u du, and then you got to replace the dx with the 1/4 du. So there's an extra 1/4 that's going to come out there. Like I said, you can do this more easily if you want. This is 1632, right? And then the antiderivative of cosine is sine u. Now I'm done with integrating. Got to add my plus c. And then I can find that's 1 over 32. Remember that u was 4x. So this is the sine 4x plus c. Almost done here. For it to be more presentable, I just want to combine these two. So I have here 2 over 8 minus x over 8 again, you don't have to be as careful. You don't have to write as many lines of calculations. I'm just trying to be thorough in the video, just so whoever is watching understands the process. And then when you're actually doing this on an exam or something, you don't need to write as much. So this is the answer. And just remember the strategy. It's the most important. Use power reducing formulas until you reach either just the cosine of some angle or a sine of some angle. That is the key. It would be very easy to change this question, like I was saying, into a question where one of the powers is odd. So instead of doing this, you should do the substitution strategy. So make sure you understand what needs to be understood.